In this 1.5 hours, we have Professor Kao Yeong-Chuan from Department of Physics, National Taiwan University, who will give us talks about what is the so-called chiral anomaly and what has it to do with the quantum Hall effect and hence topological insulators. Let's welcome Professor Kao.
Good afternoon, everyone. So can you hear me? Back? Okay. Can you see this screen?
Yeah.
This is a school on Spintronics and topological insulators. I myself am not a condensed matter physicist, but I think most physicists are, and terribly fascinated by this subject. And I realized through reading the literatures that a very interesting, some might say subtle and intriguing concept, the so-called chiral anomaly, play a very interesting or important role in understanding topological insulators. Or more accurately, I should say that chiral anomaly play an important role in understanding quantum Hall effect. And as you may have heard already, or you will hear in other lectures, or in my lectures, that quantum Hall effect is intimately connected to topological insulators. So I think it is not a bad idea to begin the school. I think my talk is the first theory talk. Okay, I don't know whether they really separate the talks into theoretical talk, experimental talk, but certainly this is a theoretical talk. Okay, the first theoretical talk begins with a discussion on chiral anomaly. There is a famous review article by two of the most active players in this field, Qi Xiaoliang and Zhang Songchen, called Topological Insulators and Superconductors. This is published in Review of Modern Physics. I suppose most of you know about this article. Okay. And their first diagram, I show it here. Okay, they show these two graphs. Okay. And this lecture is mainly about the physics behind the left graph. And I will leave other lectures to tell you more about what is quantum spin Hall effect and topological insulator problem. So I will show this graph again at the end of my lecture, so you can see why I say so. Okay, and as you can see that there is a very strange formula, 2 equal to 1 plus 1, and I wish to explain what that means. So this is these two graphs I take from also a review article by Hong Kong, and the title is Quantum Electrical Transport in Samples of Limited Dimensions, and this article is in American Journal of Physics. Oh, by the way, I will quote many papers, and I usually just list the authors and the title. And I think in the days of Google, you can, if you just copy down the author and the title, you can easily find the reference. Okay. Usually, I think all of it, I would say, are very good to read for pedagogical reasons. So I can recommend all my reference to the students. In this article, for example, okay, I will get into details in my lecture later. This is the so-called quantum Hall device, in which we are dealing with two-dimensional electron gas. Let's not worry about how experimentalists have been able to make such devices. Okay. So for conceptual viewpoint, we just accept that there exists such kind of systems, a layer of really a pure two-dimensional layer of electron gas. And as you know that if you put the system in a strong magnetic field, then you can observe the so-called Hall effect. And you can measure the Hall voltage and through it, and the Hall current. You can measure the Hall resistance or Hall conductance, and you can see that the Hall resistance is expressed in this very fundamental unit, h over e squared, and divided by an integer I. Okay. And this is a very accurate number. Experimentalists found that one can measure this number because h is a fundamental constant, e, the electric charge, is another fundamental constant, and h over e squared is important in many, many ways. And they can measure through this method by quantum Hall effect. You can measure this number to up to 1 to 10 to the 9th part. Okay, so it's so far I think one of the best number we can have is by the quantum Hall measurement. Okay. And I will explain how this comes about. Okay. And another system is the one-dimensional quantum transport. That is somehow you can squeeze the current through a very narrow channel and effectively regard the current as a one-dimensional current. And again, you measure the voltage drop and the current and find the conductance. And it turned out to be e squared over h times 2 times another integer. And compared to the Hall conductance, they share the same fundamental constant, and that is e squared over h. And the difference is nu is a constant and n is a constant. So there is a difference of factor of 2, and I will explain that why that is. And my lecture will try to explain the physics behind such systems and tell you why the chiral anomaly is the unifying theme behind this. First, about the word chiral anomaly. Let me quote the famous condensed matter theorist Phil Anderson from one of his Physics Today column articles. This one is about 13 years ago, okay, in Physics Today. And the title of the article is Brainwashed by Feynman. And what he meant was that because we physicists are so well overwhelmed by the power of Feynman diagrams that we sometimes regard, we think that all physics can be obtained from Feynman diagrams. And he cautioned us against that habit. Okay, so he said that we should not be brainwashed by Feynman. Presumably, he must give some example, right? So, what kind of effect this cannot be obtained from the computation of a or a few Feynman diagrams. Okay. And Anderson's example is the chiral anomaly. And he said in this article, okay, the chiral anomaly of quantum field theory is an even subtler effect. And you will see how subtle it is at the end of this talk. Which Roman Jacques, you will also know his work later. Okay. Explained neatly in his lecture. Anderson was referring to Jacques' lecture at the occasion of Dirac medal. Jacques got Dirac medal maybe 1 or 2 years earlier than year 2000. Okay, so Anderson said, where one expects the current of right-handed and left-handed massless Dirac fermions to be separately conserved, I should say that I will explain what this terminology means. Okay, in my lecture, I'm just still warming up. Okay, just beginning to introduce my title. So Anderson said that when we expect the right-handed fermions and left-handed fermions to be separately conserved, in fact, it's only their sum, the so-called vector current, that is perfectly conserved when there are interactions. And as a result, of things that happen at high energies within supposedly inert sea of negative energy state, that is Dirac sea or Fermi sea, as we will see. So he said that something funny happened. That is in contradiction with our expectation. And this subtle effect will be responsible for the decay of pi meson. And he says something like the mass of pi meson is not completely accurate, but well, he's not a scientist, so we will forgive him for such inaccuracies. And so why he mentioned this? He said this, okay. Remember that even nowadays, high temperature superconductivity is still an important area of research, okay. And Anderson himself was a major player in trying to understand the mechanisms of high TC superconductivity. And Anderson said that the notorious linear T resistivity observed in the cuprate is likely to be a manifestation of this kind of decay. So Anderson conjecture or guess or hint at the connection between chiral anomaly and the so-called linear resistivity in high TC. Okay. And he did not give details. He just said that it might be related, and I don't know whether he succeeded or not. But the point of showing you Anderson's remark is that at least I hope that I can make you understand, according to Anderson, the subtle effect in quantum field theory better, so that you will not be puzzled from now on what chiral anomaly is. Okay, so the word chiral, this is an adjective, okay? The noun is chirality, and it comes from Greek origin, and it means handedness. Okay? So chiral means left or right. And in nature, we can see lots of left-right asymmetric objects like hand. Okay, this is right hand, this is my right hand, and this is my left hand, and they are not the same. Okay, and in particle physics, if a fermion, like for example, if we are talking about neutrinos, we know that neutrinos are massive, but let's say that because its mass is so small, let's for the moment say that neutrino is massless. And if a massless neutrino is moving toward right, so this is the direction of momentum. And if the spin is also along the direction of momentum, we say that this neutrino has positive helicity. And later you can see that in the case of massless fermions, helicity and the chirality are the same thing. Okay, so this is a positive chirality state, and if the spin is opposite to the direction of momentum, and this is a negative helicity state, which is the negative chirality state. Okay, and so this state is not left-to-right symmetric. And as you know that one of the major discoveries in the 20th century is that parity is violent in weak intention. That is, only left-handed fermions, neutrinos, got involved in weak intentions. Okay. So the universe does not have exact chiral symmetry. It's not chirally invariant in the case of weak intentions. But in the case of electromagnetic intentions, it is chirally invariant, as we will see immediately. Okay. So first, I will tell you some formal stuff and also some history. By formal stuff, I mean you must know what Dirac equation is. Okay. So for the moment, I'm staying in the 3+1 dimensional Minkowski space world. Okay. Later, I will descend into 1+1 dimensional world and 2+1 dimensional world. Okay. So for the moment, just standard Dirac equation, and this is the Dirac equation, and d mu is the derivative with respect to x mu, and mu refers to time, that is x0, and x1, x2, x3, that is x, y, and z. Okay, so this is first derivative, and Dirac found in 1920s that if you would like to have a relativistically invariant wave function, you need to as we know that Schrödinger equation is second derivative, contains operator that is second derivative in space and first derivative in time. Okay, so Schrödinger equation cannot be relativistically invariant. And so to have a relativistically invariant theory, you either make time derivative second derivative, or make spatial derivative a first derivative. Okay, and Dirac took the second route, and he said that okay, and here gamma mu is the so-called Dirac matrices. I suppose many of you know about this, but in case some of you haven't heard this before, you can regard Dirac matrices as generalizations of the famous Pauli matrices. Okay, so they are 4x4 matrices, and the anticommutator gamma nu anticommutator, that is, this is equal to gamma mu plus gamma nu, and is equal to 2 eta mu nu. Eta mu nu is the Minkowski metric. Okay, and certainly psi is a matrix. Okay. Now I'm using the so-called Einstein convention. So gamma mu d mu means gamma 0 d 0 and the sum over I, gamma I di. Okay, and also sometimes people also write this as d with a slash through like d slash. So this is a Dirac equation. Okay, and I haven't yet put in any interaction, so this is just a free Dirac equation. And the energy, if you try to find the plane wave solution to this equation, you can find that immediately, very easily find that the energy of a Dirac particle is equal to plus minus square root p squared plus n squared. P is the 3 momentum. Okay. And if m equal to 0, the energy is equal to the magnitude or minus magnitude of momentum. So this is linear in P. Energy is linearly related to P. And nowadays, maybe I would say that 10, 20 years ago, people would say that this kind of dispersion relation can only be found in energy examples, energy physics. But nowadays, it is condensed matter physics that provide us many, many interesting examples of such dispersion relation. Okay. When I say that this is formal stuff, I mean that you just know that no such things. Okay, I don't expect, if you haven't seen this before, I do not require you to understand immediately. Okay, because I will give you a concrete example later. Of course, in a simpler setting, that is in 2 dimensions. Okay. Now, I can define a matrix. I call it gamma phi. Okay, and it is equal to I gamma 0 gamma 1 gamma 2 gamma 3 multiplied together. Okay. And I can write my Dirac spinner, that is the 4x1 components wave function, as 1 plus gamma phi over 2 psi and 1 minus gamma phi over 2 psi. This you can regard as a projection operator. Okay. And I call this part of psi as psi r. Okay, that is, I define it as the positive chirality part. And 1 minus gamma phi over 2 psi as psi L. And for massless particle, one can show, I will not show it here. Okay. This part is just the positive helicity state. And this part refers to the negative helicity state in my previous transparencies. Okay. Okay, I can, this is some definition. Psi bar is defined as psi dagger Hermitian conjugate times gamma 0. And one can show with such definition, psi bar gamma mu psi can be separated into psi bar L gamma mu psi L plus psi R bar gamma mu psi R. So you can see that this object, and it meets a current because it carries a Lorentz index. We will see what that means. Okay, again later. The left and right are separated; they are not mixed. On the other hand, this term psi bar psi, the left and right appear together; they are mixed. Okay, psi bar psi is psi L bar psi R plus psi R bar psi L. And so we can see that without such term, okay, if we, I will, in the next transparent we'll see more, okay. Since this is so, and it is easily, this is just the same, right? Because this is just the same. Psi bar d slash psi is just psi L bar d slash psi L plus psi R bar d slash psi R. Now, if we put in interactions, and I suppose that you have learned in your E&M and quantum mechanics courses that, okay, the concept of so-called minimal coupling. Okay, this is the gauge invariant coupling between psi particle, fermion, okay, a Dirac spinner, and a gauge field, A mu. So A mu is, you can regard it as basically as photon, okay, photon field, the vector potential. With this identity or this identity, we can see that this Lagrangian can also be written, this part is also the sum of two parts, precise left bar, dot, 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 precise left, plus precise right bar, dot, 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 precise right. So left and right are separated. What this means diagrammatically, okay, I'm sorry to Phil Anderson, okay, Feynman diagram is really powerful, okay. So it means that if a photon interacted with left-handed, right-handed fermion, okay, the right-handed component of an electron, for example, it will not change its chirality. The electrons will not change its chirality or handedness or helicity. Okay. Likewise, if a photon interacts with left-handed fermions, the chirality will not be changed. Okay. So that means that if you begin with an initial state which has a fixed number of left-handed fermion and right-handed fermion, and each separately are conserved in this interaction. Remember, I do not put in a mass term. I did not write a mass term. Sorry, maybe I should. So this is for massless. This is for massless fermion. Okay. If the fermion is massive, then the Lagrangian contains a term n psi bar psi. N refers to the mass of the fermion. Okay. And as you can see, that with the existence of such a term, then right-handed fermion can turn into left-handed fermion. Left-handed fermion can turn into right-handed fermion. So the number of left-handed fermion and the number of right-handed fermions are not separately conserved. Okay. But we do not want to do that. So for the moment, we say that chirality is conserved. So the theory is chirally invariant. I will immediately tell you more about that. Okay, before I go on to discuss chiral invariance, I remind you of a very important concept in physics and mathematics, the so-called Noether theorem. That is, there's a one-to-one correspondence between symmetries and conservation laws. For example, if the physical laws are invariant under time translations, then the phenomena governed by such physical laws, the energy is conserved. Similarly, if physical laws are invariant under spatial translation, then momentum is conserved in phenomena governed by such physical laws. Okay. And an angular momentum is related to the invariance of physical laws under rotations. Okay. And I think these are also very basic notions you are well aware of. Now, some of you may not know that charge conservation, certainly charge conservation is the first lesson you learn in E&M course. The charge conservation is related to phase invariance, and we will see immediately. Okay. So let me go back to this Lagrangian. I just show you. Okay. So I specified that the mass of the fermion is 0. So Lagrangian is I psi bar psi gamma mu d mu plus I E A mu. Okay. Now, this Lagrangian is invariant under two transformations. I state this without proof. Okay. Although some might say that it is so obvious that I may not write everything out. Okay. Okay. So the first transformation I'm interested in is that if you change psi into psi prime equal to e to the I theta psi, theta is some real number, a constant. So I call this transformation global phase transformation. Okay. The phase transformation I referred in the last transparencies.